Preview on the key concept. So there are many key concepts. The first thing probably is how do you compute this? Okay, this is the first important thing. This is even before convexity. Because for non-convex problem, you can also do gradient descent. It just didn't converge to global minima, but it still converges, right? So this is before convexity. And why this is important? I just randomly make up some function, okay? What is the gradient of this? If you don't know how to find the gradient of this, then you can't even do gradient descent, right? So suppose I want to minimize this. Of course, you could argue, who minimizes this? Why you minimize? No. The point here is not about, is this function meaningful? No, the point here is mathematical. It's like, do you know how to find the gradient of this? That's the idea. So we need to know how to find the gradient. Then how do you find the gradient of this? There are many ways. You can check something called matrix codebook, but I'm very sure matrix codebook don't have this function. What about put a square root here and then sign this? Matrix codebook don't have this, right? Then you need to know the math of calculating this. Then the idea is chain rule, product rule. So we will talk about how do we find this. Yeah, so that's why the first thing is about gradient or differential, okay? Then what's the second thing? So we will have convex set and convex function, okay? Again, today is just introduction, overview. So it's not detailed. So now I just give you the idea. So what's a convex function? This is a convex function. This is a convex function. This is a convex function, okay? And this is also a convex function. This is, okay, so what does it mean? This is convex. Okay, you may think, oh, convex function means I can have a line like this, joining 2 points, is the curve is below the line, yes. Or I can say this is convex because the set, after I put water inside, this is a set, this is a convex set. Or this is convex because every point on this graph, I have support below the function. If I can find this, then this is convex. This is not convex. Why? You can use this argument. Okay, this point and this point is not crossing. But if I do this, it's the same as at this point, I do not have a support. Support means something below it because I cannot cross over here, right? So therefore, this function is not convex. What about this? This actually is indicator function. This is saying that, okay, 1. So what is it? This is if x is 1, is 0. If x is not 1, it's positive infinity. Then you now see you cannot use this argument. You don't know how to draw. You can't draw, right? Come on. And then what? You also cannot do this argument. Come on, how do you write a line here? If you draw a line here, that means you have a line here, but what about here? Do you have something? What about this one? So, you see? So we will also describe how do we tell is this convex or not? Quick answer, this is convex, okay? Then there will be some funny thing. For example, this is number 1. What about union number 2? Is this convex? This is not convex, but how do you tell this kind of thing, okay? Then once we have convex function, convex set, 1 and 2 together give us gradient descent. Okay? Because once you know how to find gradient, and you know it's convex, that means one gradient descent give you function value going down, and then by analysis argument, what? So again, this is a preview. So you have xk equal xk minus step size. Okay. So now for simplicity, let's assume alpha is always 1. Okay. Just assume it works. Okay. I just assume this. Now what? Then from this, I will have what? Function value at x1, function value at x2, function value at x3, blah, 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 right? Under some condition, I can show this, right? Then what? If I can also show f is larger than 0 for all x, then I have this, right? Then what is this? This is iterate. I have this is going down. It bounded below by 0. Then it's the same as I have a sequence, monotonically going down, and AK is bounded below. Then I forgot the proof, but you know, then this means A converge, right? I forgot the full proof, but then you know this converge. Then this means what? This means f x k for k go to infinity converge to something. Here's important. I just said it converges to something. It does not necessarily converge to the minimum value. It can stop in the middle. For example, it can just stop here. It never go to here. Right? We don't know. So that means we need more to tell when will this converge to minimum. Because converge does not mean converge to minimum. It can stop in the middle. Okay? So this is the first thing. So this is gradient descent. This is detail. That means how should we select step size? How should that means what is this alpha here? There are theorem. For example, I just let you know this for a moment. If this thing is L Lipschitz, so what does it mean? Lipschitz means we have this. This means gradient is Lipschitz and L is the Lipschitz constant. If this is true, then alpha, this always works. Yes, and actually alpha, any number between 0 and 2 and 1.99999 something always works. Yeah, something like that. So yeah, it works. That's the theory. And then we'll talk about how do we take step size, how do we select step size, and how fast it converge. And actually this will go to also Nesterov acceleration. Okay. So this is the second key point. And then this actually is for min f. What's min f? No constraint. This is actually what I talk about in this picture. No constraint. So actually it's just here. Okay. Then we have this picture, right? So we have the move, right? So that's what we will go later. What we will go first, it will what? We will go to projection prox for what? For min x in C or min f plus g, where g cannot differentiate. So this will also give us subdifferential, which is actually what? The complicated version of 1. So this is a complicated version of 1. So at 4 we go back to 1. Okay? That is what is a subgradient, what is a subdifferential. And that's it. And now we can now deal with what? Constrained optimization and non-differentiable optimization. And then this is good because this is unconstrained differentiable. Now we can do constrained differentiable or no constraint but non-differentiable. Then you may ask, what about if I put an x in C here? Good. This is what's next. So what happens if I mix all of them? Then we will talk about duality and conjugate. And this is a problem. This is the math. What's the algorithm? It will be ADMM, Lagrangian multiplier or augmented Lagrangian multiplier. And then we have a bunch of something called hybrid primal dual algorithm. They have a bunch of people's name. And then they also have something called splitting. So basically, it's just all of them are primal dual thing. Yeah. So that means, let me try to recap. So 1 and 2 is not optimization. It's basically convex analysis. It's for the optimization in 3. Once we reach 3, it's optimization all the way. But sometimes we go back to the convex analysis. For example, we need subdifferential. Know what the heck is subdifferential, and we also know what the heck is duality, what the heck is conjugate, and what the heck are these. So this is basically the whole thing. Then these are the 5 things. What about the 6th one? There's no 6th one. These are basically the most important 5 things. How to find a gradient, the characterization of convex function or convex set, convex optimality condition, and then all the theory of gradient descent, all the theory of what? 2 special versions of gradient descent, the proximal or projected gradient descent or primordial gradient descent. So you may think of ADMM, oh, it's something else. No, actually ADMM is just some special primordial gradient descent. It's actually primal gradient descent, dual gradient ascent. So basically it's just 3. Okay, so this is the thing. And once you know 1, 2, 3, 4, 5, you basically know many of the other things, including what? Including how do you do stochastic gradient, how do you do DC program, fractional program, or multi-objective, or distributed, or even manifold, or biconvex. It's the generalization of everything here. So these are the most important part. So after this part, as I showed you previously in the long document, the last chapter is all problem. I just describe it slightly and then that's it, because no time. So these are the technical details. So now I go to each of them, talk about it a little bit more. Well, the first thing, this thing is we need to know about something called Gatot derivative or Fetched derivative, whatever thing. So it's like this. You have an x. Now I have a small number called t, and then you have a direction. So it's a directional derivative. Okay. So if I have this, then this is directional derivative. These are all vectors. But now I have a linear map. I call it L. It's not Lipschitz constant. Let's just call it L. Okay. And then what? And then together with this directional derivative, I call it T. Okay. Actually, I should put something here, but doesn't matter. So I'm now going to, norm this using norm instead of function value minus each other. Then, something like this. Then I want this to be 0. Then this L is the gradient. This is the directional derivative or general Gatot or Fetched. I forgot which is which, but anyway, this is the starting point. And this is the definition on how we compute this. And this actually gives us the following, that is, how do we compute partial derivative? Why we stack partial derivative give us the gradient? Because of this. Okay, so this is starting point. Okay, and then what? Once we know how to calculate this kind of gradient, then we will now talk about what's the chain rule, product rule, quotient rule in this case. So that means what happens if I have this? Yeah, I have this, then it will be what? It will be, this is actually a Jacobian, okay? And then something like this. So it will be what? Imagine this is a matrix, so it will be J, something like this. So it's like chain rule in the one variable, but now we have matrix multiply a vector. And you use this to simplify the stuff. So it's like this. So an example. Okay, maybe you know this very well, okay? This is what? A transpose AX minus A transpose B, something like that, right? But actually, then what about this? In terms of this, the answer is this. So you have a linear map, go out, transpose. This actually is chain rule or product rule, something like that. We'll talk about this later, okay? And this is very useful for calculating gradient. And this is a must, because if you don't know this, then how do you calculate gradient, okay? So this is basically the first part. Then once we finish the first part, okay, then we go to convex function. So because a function is convex, we will have this, okay? Yes, if a function is convex, this will be true. What does it mean? Just give you a picture. I have a function here. This is not one dimension, this is any dimension. I just draw in a line, okay? This is a point, okay? This is a point, x. Then this is the what? The function value fx, okay? So this thing is this thing. Then what's next? I have a y, okay, I have y here, I have a y here, okay? Okay, then what? This thing, I have a tangent, right? This tangent has a direction, right? This actually is gradient, okay? Okay, then what? This is saying that my fy, this point, larger than this value, okay, I call it like this, plus a straight line at the y. The straight line is this, at the y is somewhere here. So what is this thing? This thing is this line, this straight line. A straight line is y equal mx plus c, right? Slope, variable, coordinate, that fixed. Coordinate, that fixed, slope, the variable. Actually, the coordinate that fixed is this number plus these two inner product, okay? So this is what? It's a straight line. Then if a function is always above a straight line like this is tangent or support, then this function is convex. Because why? Because a function is convex, you may know this is internal description of convexity or Yang-Sen's inequality, okay? I believe this pronounced Y, I think it's German, right? Okay, and then what? This is the same as, this is a convex set. Because if I put water inside, then this is convex set. This is called epigraph, okay? And then what? A convex set, how do you describe a set convex? A set is convex if it is an intersection of many half space. So this set is convex if I have a half space. I have a half space, I have a half space, I have a half space. Then one particular half space is the tangent. So therefore, this is convex if this is true, this is convex if this is true, so there are if and only if. So therefore, I can use this to describe convexity instead of this. Because this is, in terms of algorithm, is useless. You just say, oh, it's a chord inside your function, so what? But you need gradient. So therefore, this one is better. In fact, when you prove convergence of gradient descent, you use the gradient a lot. So therefore, this is a better definition of convexity. And there are actually also other definitions of convexity. A function f is convex if you restrict it into a one dimension lower, it's still convex. So suppose you have a convex function in two-dimensional space, okay? And then you chop it by a plane, then now you see a curve. If this curve is convex for any way you chop it, then this function is also convex. Yeah, this is also a definition of convexity, but this is useless for us, okay? So therefore, that's why this is a better definition, okay? This is one thing. Then we talk about what is convex set, what's convex function. What's next? After we have this, then we finally go to gradient descent. What's gradient descent? For this problem, we have this, okay? Then these are what? Gradient descent. Then you will ask, how do I find this? Then there will be what? Amijo rule and Wolff condition. What are them? Then we talk about it. And then what? Where does this thing come from? Okay, this thing comes from Cauchy in, I think, this. But the problem is this the end of story? No, actually this thing is arc mean of something else. Then what is this? Then you, by seeing this as arc mean of something, actually you can tell what is gradient descent doing. Gradient descent is actually doing majorization, minimization. So the idea is, I have a function like this, okay, I'm now here. So what is gradient descent? Gradient descent is, I'm now here, I build a local quadratic model around my point. And then I move to the minimum of this point. Then once I have this point, I project down to here, I build another quadratic function. And then I go to the minimum. And then I'm here. So this actually is the picture of gradient descent. So gradient descent is not what? It's not, oh, I point here and then move to here and then move here. Actually, it's a bunch of curves moving down until you touch the curve, the bottom of the curve touch the bottom of your curve. This actually is what gradient descent is really doing. And this actually also explains why sometimes gradient descent doesn't work. Because for some problem, this idea doesn't work. Yes. For example, power 4 function. Then let's imagine you have a power 4 function. Okay, power 4 function like this, right? Okay. Then you cannot have this. Because this function, power 4, always grows faster than quadratic. So it's impossible you find a quadratic like this because at some point, the black thing will go over the red thing. So therefore, this is a fact. Gradient descent actually doesn't work on this. You may not know. Okay, let me tell you. Gradient descent actually doesn't work on this unless you do some special tuning or you do some special precondition or something called metric, variable metric. So actually gradient descent doesn't work on this. Yes. And therefore, actually there are lots of theorem in gradient descent. Okay, and then we talk about how to find alpha, the convergence, what is it doing, and then speed, and then how to make it faster. That's it. And then what? We have prox, project, and subdifferential is basically about how do we project onto a set C. Projection onto a set C is actually a Rn to C mapping. Because, okay, come on, by definition, it's onto C, so Rn to C. This is a subset of Rn, so actually it's Rn to Rn. And then what is this? This is actually arc mean. So it's also an optimization problem of what? Y minus Z, this is Z, this is Z, this is a point, Y in C. So basically it's saying, for all the points in C, find the one that's closest to your input point. Okay, then what about prox? Will be, I have a G here, I just add the G here. Yes, that's it. Then you may wonder, what the heck is this? Okay, I will explain later. And then prox actually is something called Moore envelope, and Moore envelope is some convex analysis thing, so not now, later. Then after we have those, we can now make gradient descent by just adding this operation on top. The reason why this works is because projection operator and proximal operator is non-expensive. Non-expensive meaning that I do the red thing will not harm the whole thing. I do the red thing, at worst is doing nothing. Better case is it improves. So therefore I can just do this. And this is projected gradient descent and proximal gradient descent. Okay, and then what? Okay, if we somehow want to put a matrix here, then we have Newton's method. But before that, we have something called preconditional gradient and then variable metric gradient. And this also linked to neural network. Some people have a method called ADAM or ADAGRAD. Actually, the idea is just you multiply a matrix here. And that matrix is not Hessian, but some funny matrix. Yes, that's actually what people do in deep learning. You just multiply a matrix here and suddenly it runs faster. Okay? And then after that, we have constraint and non-smooth. Then what about constraint non-smooth at the same time? Then we talk about duality, splitting. So this is the idea, for example, okay, so for example, ax minus b 2 norm plus lambda, cx minus d 1 norm subject to x, okay, just this, okay. How do you solve this? So this is the original problem. Then you can solve like this. This is on x, right? Now I have x, y. So I can say ax minus b, this is the same thing, no change. But now, y. And then what? I have a y, then I need to do something. I have a new constraint. Y is cx minus d. So that now I have this problem. Then what is this problem? This is f g constraint. F g constraint. You solve this by something called ADMM. What is ADMM? You build a Lagrangian. By what? This is f, this is g, and then you put this inside. So I put it inside. Cx minus d minus y, and you put a Lagrangian multiplier called lambda. And then what? This is Lagrangian, but in ADMM you work with something called augmented Lagrangian. So basically, yes, you add a penalty here. This is a tau, it's a penalty parameter. So this is an augmented Lagrangian under tau. And what you do? Then you now have this Lagrangian, augmented Lagrangian. You do gradient descent on x, gradient descent on y, and then gradient ascent on lambda. Then this thing is ADMM. Then the question will be, when does it work? When does it converge? How do you tune tau? What happens if you have non-differentiable thing, blah, 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 blah. So this will be this part. And once you know ADMM, you will automatically know what is splitting, what is H hybrid primal dual gradient, and there are a lot of other algorithms called Koda Vu and then David In's, a lot of things. And then that will be the this part. And then the sixth part will be those special formulation, convex programming, fractional programming, difference of convex programming, manifold, bilevel, finite sum, stochastic gradient, blah blah blah, lot of things. Yeah. So but that part I don't have time to talk too much in detail. So basically, the main focus is to know all the theory of 1, 2, 3, 4, 5.